a look. I mean, it's important to pay attention. So this bit of the integration we do. We leave this one that's not so interesting for us. We only focus on the integration over the soft gluon momentum. We already will drop k here, because k is very, very small, and we can drop it with respect to k and p. So we will not be bothered by the overall momentum conserving element. This is really soft gluon we're emitting. So we can approximate diagram A as IGA-TA epsilon mu of k P1 mu over P1 dot k times M0, and MB will be IGTA epsilon mu of k P2 mu over minus P2 dot k M0. M0 is the amplitude without emission. M0 is just this no emission. And this we have just derived. This is the soft approximation, the diagonal approximation on these emissions. And you see here it's actually quite nice if I then look at M in total. A lot of things are common. Epsilon mu of k, and then I have here P1 mu over P1 dot k minus P2 mu over P2 dot k, all this times M0. So this is called also the iconal current. You see it often in text. We won't be using this term too much. You see, actually, it's a nice object, because if you contract it not with epsilon mu of k mu, to check our current conservation, you get 0 right away. I don't even have to do it. So this is a nice expression. What we must now do is take this expression and compute the absolute value squared, sum over all spins. So compute sum over spins of m squared. But that will actually be fairly easy, because it's already factorized, so we certainly get m0 squared. That's sort of uninteresting, but we have to keep it along. And then we have to sum this part squared, summed over spins, and we use that sum over, well, spins lambda of epsilon mu of k lambda epsilon star nu lambda of k. This is from the complex conjugate amplitude. We can here just take eta mu nu. Anything real, if you only sum over the physical ones, you get terms with k mu, etc., but they cancel because of this current conservation. So we can really just take eta mu nu. So you can really just take this thing, square it, and then you see that the only thing that contributes is the cross term. Because this thing squared will be proportional to P1 squared, which is 0. This thing squared is proportional to P2 squared, only the cross term matters. Right. So we have here now actually a nice expression. So we get that m squared, that the integral over the phase space of k and m squared becomes, now we can be a bit more explicit, dnk over 2 pi to the n delta of minus 1 delta of k squared 2 p1 dot p2 over p1 dot k p2 dot k. That's what we have to compute. Notice, by the way, and maybe I did it a bit under the radar, I also took the phase space in n dimensions. So I've always been doing n-dimensional regularization for loop intervals, but you can also regularize the phase space in n dimensions in very much the same way. There's nothing new there. We're just realize that these are n-component vectors. Okay? So let me then show what we get. I'll do it here. Okay, have people finished writing there, or should I stand there for the camera to be on that board? This is the last line. This is the last line? No, no statistical for phase space. Oops. Zoom in. Yes. Very good. Did you get it? Yeah, okay. So we can be a bit more explicit about it. So this will be some prefactor that depends on n dimensions, and there will be 2 pi to the n. We'll all keep that there. Then we have, you see, the n-dimensional angular integral is a generalization of the polar integral formula, where you have sine theta d theta. But then you have lots of these sine thetas, and you have n of these angles in high dimensions, and to various powers. Almost all are irrelevant, except for one. That's the one which signifies the dot product between k and the direction of p1 and p2. That will be the z direction. We only need one angle, right, between the k and that z direction. All the other thetas don't occur in the integrand. So that's inside the Cn. And then the last of the integral is theta n sine to n minus 3. It's also in the lecture notes that you got, how to do an n-dimensional angular integral. So this is the Jacobian factor in n dimensions for the last of the integrals, of the angular integrals. And we must also do the integral over the size of k to the power n minus 2 occurs here, dk. And then we have this delta function of k squared, which gives you 1 over 2k0. But recall that k squared is 0. That means that k0 is equal to the absolute value of k. It's on shell. So here we have a factor of k, which is really k0. That's the phase space. And then we have our integration measure, and that is just 2 s hat p1 to p2, and then here k vector squared 1 minus cosine squared of theta n. Right, you see this? We have that p1 dot k is p10 k01 minus cosine theta n, because this is p is in the z direction. You get 1 minus, and p2 is in the minus z direction, so you get exactly the same with the plus there. And you multiply and you get 1 minus cosine theta n squared. So now, what do we see? Well, we clearly have sort of a factorization of integrals. Now, what does the k integral range from? Well, it can be as small as 0, right? We're dealing also with an infrared limit. Now, it cannot be infinite on the other end, because it's a phase space integral. There's not a loop integral. There's always at some point a maximum energy. So we'll call the upper cutoff q, where q is some typical phase space variable that provides the upper limit on energies you could possibly have. But it's not infinite. There's no UV divergence in phase space integrals. And this one, well, it goes in principle from 0 to pi. Now we can do the k integral first. Let's see. We have here dk, k to n minus 2. This makes it n minus 3. This makes it n minus 5. So if we have a dx x to the n minus 5, the primitive is 1 over n minus 4. Right, so for the k integral, we get 1 over n minus 4 times q in the power n minus 4. which is nothing but epsilon. So we have here the infrared divergence in phase space. And then we have here, we can do the other one too. And you notice, by the way, that dimensional regularization has regularized the infrared divergence. We did not get infinity, we got net 1 over epsilon. Here, in the angular integral, we get n squared n minus 3. Now we can all rewrite this as sine squared. So you get n minus 5. Now for very small theta, when you're in the nearly collinear region, this behaves like theta n to the power n minus 5. That's again goes like 1 over n minus 4. This is a bit more tricky because well, we're looking at the collinear limit. I'm just trying to get the divergence out. So you see here really a double divergence. This is a 1 over epsilon from the collinear, and this is a 1 over epsilon from the infrared. And they can occur together. You have a product in this extreme case.
From UV side, there will not any variable is such that added is to epsilon square. In UV case,
Just a single power of 1 over epsilon, that's right. You cannot have this overlapping divergence. So, roughly speaking, from the phase space integral, for this soft collinear gluon emission, so the result, this is the structure of the result, is 1 over epsilon squared q in the power epsilon in the infrared limit. Just to give, I mean, there's also m0 squared, but that is more or less the answer. Now, let me also give you already one hint that if you can rewrite this as 1 over epsilon squared plus log q with 1 over epsilon plus 1/2 log squared of q squared plus 1/8 epsilon log cubed, etc. You know this. So if you realize that eventually we will get rid of the divergences, then the thing that remains is the log squared. That's a finite leftover from the infrared cancellation. And this q is not necessarily always some scale, the mass of something, but it's a limitation on phase space. So it could be, for example, that q goes like 1 minus z. The extra energy left over, z is the Drellian z, and then you find the log squared of 1 minus z here. So in other situations, we could have that it's in transverse momentum summation, in transverse momentum case, that you look at the transverse momentum of some particle you produce, that you look at the very, very small pt limit. Say it goes like pt over some large scale q. And that way you have a log squared of pt. So depending on what the phase space really looks like, what you really put up here, that depends on the realistic observable you look at. The same mechanism of infrared collinear cancellation can produce different types of logs. And those occur, as you see, systematically, order by order in perturbation theory. And if I do this at second order, I would get 1 over epsilon to the 4th. And then the finite term, the remainder would be a log to the 4th. Unify, etc. You see the pattern emerging just because at higher orders you get higher powers of divergences. You get immediately also higher powers of logs. The two hang together just by this expression. Right? So this is an important insight, I think, to have. Now, I told you that a bit about the mechanics of it, how the combination of how this integration over phase space, when the extra radiation that you include becomes collinear and or soft, produces divergences and accompanying logarithms. What I haven't told you yet is how to get rid of these divergences. If they're interesting in and of itself, then we can love them and really think about them a lot. But if they're there in your answers, then it's all useless because the perturbation theory again is not predictive. So how do such divergences, infrared and collinear ones, in the end get removed or cancel in cross sections? That's the question I want to address now. So how do these IR divergences, and IR again I mean both soft and collinear, cancel? That's the question. Well, one answer is not through some kind of renormalization, not through some new renormalization of the Lagrangian in QCD. We did that to get rid of UV divergences. And the nice thing is if you renormalize things in Lagrangian is not an observable. If you do it there, it works for all observables. We cannot do a sort of extra renormalization on top of it to fix this. It doesn't work. So, but to the aid comes the theorem called the Kinoshita-Lee-Nauenberg theorem. And Kinoshita is in Cornell. Lee is T.D. Lee from Lee and Yang. He's in Columbia. And Nauenberg, I think, at Seattle. So, yeah, so they say IR divergences cancel. When combining loop and real emission diagrams. For a cross section. So for amplitudes, they don't cancel. If you just have an amplitude with only virtual loops, it just may be divergent, even after renormalization, but it will have infrared divergence. Only when you start making cross sections, observables, will you get a cancellation of divergences from the loop integrals and the real emission ones. So in the loop integrals, we got divergences because we integrate over loop momentum. And certain regions of loop momentum space gave us divergences. We cannot restrict loop momentum, we must integrate over it. And here we've seen that you get, if you cannot observe the gluon because it's too soft or too collinear, you must also integrate over it. That also produces a divergence, and the two actually will cancel by the KLN theorem. You can appreciate that this is often appreciated as KLN. Now the real content, so cancel when combining for cross sections. And this doesn't have to be total cross sections. This can even be differential cross sections, if defined properly. So this is called infrared safety. In words, if you define your observable such that this cancellation occurs, it's infrared safe. And with that I mean also collinear safe. That is not always in triviality. In the Tevatron D0 and CDF, for some years we're using a jet algorithm that turned out to be not infrared safe. That was fixed. But it is this in order to let this theorem operate in order for the divergences to cancel. Now, the real, maybe worthwhile phrasing it a bit more precisely. IR divergences. This is what KLN say. IR divergences. Present in part of the transition. With that I mean scattering. amplitudes cancel when averaging over a suitable set of degenerate states. So this is a theorem worthwhile writing out in full, because it's so important to the predictive power of QCD. Without this theorem, we'd be sunk. The way it's phrased also hints at the fact that this is actually a quantum mechanical theorem already. It's not only true in QCD or in field theory, it's even already true in quantum mechanics. Quantum mechanics also has infrared divergences, but and the proof actually in the original papers, I think at least one is in quantum mechanical language with degenerate states and perturbation theory 1 over E minus E prime type things. You can show that it happens already there. And there's a field theory book by T.D. Lee. It's actually a very good book. It's a bit older. It's horrible typography, but it's worth reading. It's a very good book to look at. It has a black cover. So, for example, let's look at E plus E minus to anything. The total E plus E minus cross section at NLO, at next to leading order. Now, what is and X means anything QCD-ish, any kind of QCD type final particle. Experimentally, that means hadrons. For a theorist, that means partons. So you start off with Q bar. That's the simplest thing you can do. And this is E minus E plus. That's the lowest order cross section, the lowest order approximation to this. The next to leading order then would be a loop direction, also another loop direction, this, and etc. There's also one on the other leg, but also the final state emission. So this is more or less the sort of final state version of Brillouin. All of that contributes, and you must look at m squared, right? This is what Philosophers and now will tell us. So square. And what I'm going to do is square is m dagger m, or m star m. These are the diagrams contributing to m. I'm going to be drawing m star as well, but flipped. So this will be, and separated with a line like that. So this is E minus E plus, and here's E minus E plus, Q, Q, Q bar, Q bar. So this M dagger. The Hermitian conjugate turns all the lines around. And you sort of see a nice matching up of final state particles. It's actually called cut diagram notation. It has interesting rules in and of itself, but I will not go into that. So this is the first part of m squared. And then we have, let's do these first. We have so that's this diagram squared with itself. We also have, let me just draw it this way, this going like this one combining with that one. You have a sort of interference term. And two more of these. Okay? So this is when this one interferes with that one. And then there are these. Now, do I get those squared? Yeah, so this, what you get at this order is not this thing squared, but the interference term only of this with the Born, because I only want 2 extra powers of the coupling. You have 1, 1, 1, 1, that's okay. But here I need this, because this is also only 2 powers of the coupling. If I had also the loop here, I would have 4 powers of the coupling. That's part of the NNLO calculation, which we not do. So loop only occurs as an interference term. So we have here 2 contributions. Of course, I haven't drawn all of them because there's also the one where the loop sits here. I've drawn only some of the contributions. Now, the question is, are we summing here over degenerate states? Can we assume that Kinoshita-Lee-Nauenberg holds? Well, if we look at the total cross-section, you know, you can't get more inclusive than that. Right? So if there's any degeneracy, it will certainly be in the sum over final states, because we sum over all final states. You can also sort of see if this becomes very, very collinear. This is actually the calculation we just did there, right? This interference term. And this, when this becomes very collinear, then it is more or less the same phase-space region as this, except this gets reabsorbed on the line, this gets emitted, but it's the same type of collinear divergence. So these two indeed are very, very similar. And since we sum over all final states, they are included in the set of degenerate states if the extra gluon is very, very soft and collinear. So that would be okay. So KLN here is okay. In the sense that, yes, very, very soft or very, very soft, very soft real or very, very soft virtual emissions are degenerate with each other. It's almost exactly the same final state. And both these final states are included because we sum over all final states in the total cross-section. So, but it's a bit boring if we only could do final total cross-sections. So, is it also true if we look at less inclusive cross-sections with a bit more structure in the final state? So for total cross-section, sufficiently inclusive, KLN holds. But also okay in more restricted settings. Cases. For example, and now I'm being even more cartoonish than before, let's look at E plus E minus E plus, making 2 jets. Now what is a jet? A jet is you define a direction and include directions near it as well, and sum of all particles in that jet cone. You call that still part of the same signal. It's part of your same, it's degenerate with the main state. So anything, so if I draw here a little cone, this together with any kind of collinear emission is all still in the jet. And if you look for a jet cross-section where the jet goes in this direction, the jet has a certain size, then all collinear radiation is included. But also, virtual corrections are included, obviously.
One question: if we need to add all soft emissions, that's going to get finite cross section. All.
No, you do it order by order. You don't have to add them all.
Okay.
Just per order it works. Yeah. So this is also okay. So the KLN also works here. And this was a very nice realization also in the mid-70s, I think. So we'll start with Sturm and Weinberg jets, and then later on. Our jet definitions are no longer really actual finite angle geometrically defined, but now you can define them algorithmically as well. You define them through a jet algorithm, which more or less approximate such a cone, and it's good enough for having KLN being operative. So that's how we get rid of infrared and collinear divergences, through the KLN theorem. We don't have to renormalize. We don't have to do anything. All we have to do is make sure we work in d dimensions, keep track of our divergences, add real and virtual diagrams, and we will find that divergences cancel almost all the time. Does KLN solve all IR problems? And the answer is not quite. So it's okay for final state. So anything with final state divergences. In the initial state, collinear divergences can remain. And as long as any remain, we're still sunk, right? So if we cannot handle this, no matter how beautiful this is, well, this would be enough for E plus E minus colliders. We didn't have to worry about this. But E plus E minus colliders, all QCD is in the final state, and we're okay. This problem, when you have initial state quarks and gluons, is of course the case when you have hadron colliders, either one or two hadrons. And what I'm telling you is that initial state collinear divergences do remain after you've done your calculations for real and virtual diagrams. You added them up. A lot of poles will cancel already, but there will be something left. And then the question is, what do you do then? Right. So this, I think, is for next time. Right, we're almost done. Sorry? Yeah, I think this is a good moment to stop. So that's what we'll be addressing next time, this final step of how to factorize this divergence. And I want to do it in the case of a concrete example of Drell-Yan again. Actually with the real formulas for Drell-Yan, and not just these sketchy formulas. They help you with ideas, but I want to show you, not derive, and that will be in the notes actually that you will get. But I want to show you at least the real formulas, see cancellations occur, also see leftovers be there, and then see how those get removed. And that again, as always, removing final divergences has nice side benefits too. You will find that out of this problem follows the Altorelli-Parisi equation, which is a very wonderful equation for PDFs. We'll see that all next time. So let's have tea.
Let's move on quickly.